All right, recording is rolling. So we're going to finish these puzzles. All right, the last couple we did here were the thermal expansion. There was a linear thermal expansion, and then we were looking at this volumetric thermal expansion, which is just linear in 3 dimensions. Right, so the question was framed, what's the percent change in volume? All right, we're ready to move on to this Pascal's principle question with this hydraulic lift. So number 108, zoom in here. 108. Okay, we got this hydraulic lift. You guys saw this in a presentation the other day. I'll show you guys Pascal's principle. Pascal's principle says that the pressure in this fluid down here, this radiated fluid, is transmitted undiminished. And if it's like a liquid fluid, maybe it's a little bit more pressure on the bottom than the top, but it's equal pressure at equal elevations. Okay? Now, if you know that, then see there's some pressure pushing up on the small piston, and there's some pressure pushing up on this large piston. And it has to be the same pressure, especially if it's same elevation. Now, these are slightly different heights, maybe a little bit different, but negligible if it's a highly pressurized fluid. Okay? But that's going to result in different forces. Okay? Recapping why this works. So pressure is force per unit area. So force is pressure times area. And if it's the same pressure on different areas, that's going to be different forces. So that's how with the very small input force, you can lift a very large weight on the other side. Okay. You know what this reminds me of? Do you guys remember last semester setting up those pulley systems and getting a mechanical advantage? Which I still got it set up over there. You guys see that? It's a 5-to-1 mechanical advantage pulley system. Right? So you can lift something 5 times as heavy as your input force. Now, you don't get something for nothing. Right? By increasing your strength, there's a way that you're paying for that. Do you guys remember how you pay for that with the pulley system? You can become a lot stronger, but by doing what? By pulling lots and lots and lots of string. Remember, so for a pulley system, you might pull like 5 meters of string, and then the output, that huge weight, only lifts like a meter at a time. Okay, so it was really to like a conservation of energy type thing. And I think there's like a similar thing here, because here the hydraulic lift that I showed you guys on the presentation the other day had like a vehicle over here, like a whole car that was being lifted. Right? So if you want to lift something very heavy with a small input force, okay, I could push down with a small input force. Isn't that going to displace like some volume of water, right? Some tiny cross-sectional area times the height change. Right? And on the other side, that would be an equal volume of, or I said water, but fluid. I guess whatever fluid this is, right? An equal volume of that fluid would be displaced over here, but divide by a huge cross-sectional area, it would only move up a little bit. Okay, so it looks like the same type trade-off as the pulley system, right? With a very small input force, you can lift a very large output force, or get a very large output force, lift something very heavy, okay? But only a little bit at a time. So I guess energy is still conserved. Right? Let's go through Pascal's principle for 108. Okay. So Pascal's principle. It says that the pressure on the left side is equal to the pressure on the right side. So P1 equals P2. Okay. And pressure, you guys know, is force per unit area. So that's equal. F1 over A1 equals F2 over A2. Okay. So did I give you 3 out of those 4 things and ask you to solve for the last one? Almost, but not quite. Okay, I did give you one of the forces. I told you the forces being lifted, the weight of that in newtons. I did not actually give you the cross-sectional areas. I told you the diameters of these things. Okay, so there's like one more middle step you have to throw in here. It is here. Do you guys know how to get the area of a circle based on its diameter? Oh, it's diameter d. Right. Okay, yeah, related to that. So area is equal to pi r squared. Right? And if you substitute in this diameter in terms of the radius size, isn't this radius half of this diameter? So it'd be like diameter over 2 quantity squared. Okay. And then you could take, okay, 2 squared is 4, that's in the denominator, pull that up in front. Isn't that like pi over 4 times diameter squared? Okay. So there's how you get the cross-sectional area or the area of a circle based on its diameter. So it's pi over 4 times diameter squared. Maybe that's a good tidbit, you know. I'm going to take this and substitute that and for this area, because Again, I gave you guys diameters. So this would be force, the input force divided by pi on 4 diameter 1 squared is equal to output force divided by pi on 4 diameter 2 squared. So, all right. Okay. Now, next thing that happens, this happens a lot with proportions, is that the pi over 4 part cancels out anyway. So even if you miss that detail, the important is that it's a squared relationship with the diameter, right? Right, so we're solving for this right here. What's the input force? Okay. Some point I have to plug a number, so why not now? Go ahead and plug it. So my page says the output force is 12,000 newtons. So I'm trying to lift something that's 12,000 newtons. Therefore, you need that force on the bottom of the large piston pushing up. I told you the large diameter, well, my large diameter, I should say, is 4 meters. And don't forget to square that, because the square of the diameter is proportional to the cross-sectional area. Okay. And then my here's force input that I'm solving for. My input cross-sectional area was only 0.25 meters. And don't forget to also square that. You're gonna see there's gonna be one algebra step after this point. I'm gonna take the square of the small diameter and cross multiply it up. Right? You guys can do cross multiplication, right? And then that would be the answer. Try it out here. That should be it. Double check that's an answer choice. Yep, that's an answer choice. Pascal's principle. Yeah, cross multiply. So if you want to isolate this F1, right, take this denominator, 0.25 squared, and cross multiply it. So multiply it up here. Okay. I do it inside here. You guys have A over D equals C over D, and you're solving for A. Just basically what we're doing. Right? Take this B and cross multiply it so that A is equal to C over D multiplied by D. Yeah.
If you're watching video at home, let me pause this real fast.
Recording is resumed. Okay, so next one. Oh, actually, we got a pair of questions to end this page. Okay, these two go together. They both refer to this diagram. I got a pipe with water flowing through it. Okay, you guys see a large pipe connected to a small pipe. The first question is conservation of flow. And then you have to get that one right to answer the last question, which is a Bernoulli principle question. Okay, so start with the conservation of flow question. Think about what happens to the speed of the water as it goes from the large pipe to the small pipe. How many of you guys think the water has to speed up when it goes from the large pipe to the small pipe? It's going to speed up, speed up. Yeah, you're right. It would go faster. And tell you what, if you're not 100% convinced, then we remember one tool for your mental toolkit that you can get out of a class like this is taking variables to extremes. So what if the large pipe was like the ocean and the small pipe was like a little straw? Guys, if you're pumping the ocean through a straw, isn't the ocean basically not moving and the straw is like a bunch of water rushing through a straw? Right? Or if you have water flowing through a straw out into the ocean, when it hits the ocean, basically comes to a dead stop, right? Okay, so maybe that can help give some kind of context. But here's what I did. I'm gonna rederive for you guys conservation of flow, and then plug in these numbers to actually solve this thing. Okay, so D1, conservation of flow. I'm thinking that say just to stick to American units, like gallons per minute would have to be constant throughout the system, like the gallons per minute. isn't that some kind of volume per time, right? Volume per time. So volume 1 per time 1 equals volume 2 per time 2. Okay, so gallons per minute, cubic meters per second. That's constant everywhere in the pipe. That's why I'm saying it equals, right? But that is conservation of flow. Okay. Now, volume. Could I do that as like cross-sectional area multiplied by the distance that the water goes? I mean, area, some cross-sectional area multiplied by some distance the water goes. That would represent some kind of volume, right? Per time. So A1 X1 on T1 equals A2 X2 on T2. Okay. So this is this. You guys see that? Again, gallons per minute, cubic meters per second. That's the units we're talking about. But then you just group these variables together a little bit differently. So what is distance per time? What's that called? Like velocity, speed? Okay. Okay. So cross-sectional area times the speed is also the same everywhere. Okay. So there, that's the version of conservation of flow that we're actually going to apply to this problem. Because I gave you 3 of those 4 numbers. Actually, did I? Yeah, I did. I want to make sure that I gave you the cross-sectional areas instead of diameters, because that's another way you can go to, just like the last question with the hydraulic lift. Sometimes you get diameters and say, oh, well, I need to square that. All right, so popping some stuff here. I told you the large pipe cross-sectional area. That'd be, for me, it's this many square meters. And I told you the initial speed. So for me, it's this many meters per second. And I told you the cross-sectional area of the small pipe. So solve for the second speed. You guys see, the one math step you need is to take the second cross-sectional area and divide down on the side. So for me, it's going to work up to this many meters per second. Yeah, the water definitely did speed up. That speeds up inverse proportion to how the cross-sectional area changes. The fact that my cross-sectional area decreased by a factor of 4, well, the speed had to increase by a factor of 4. Conservation of flow. Okay, that working out for you guys? There we go. Now that one you have to get right to get the next question. This is really a lead into the next question, which is the Bernoulli principle, okay? Which has to do with pressure. Okay, so now we're getting to the part of the story. Imagine that you're a fish swimming around this pipe system. There will be a pressure change going from the large pipe to the small pipe, where the water speeds up. Do you guys remember what happens to the pressure when there's a moving fluid? Is that a pressure increase or a pressure decrease? How about this? I'm going to take this page of notes. I'm going to blow a stream of air over the top. Okay. And when I do, it's going to do one of 2 things. That moving air, either it's going to push it down or it's going to vacuum it up. Do you guys remember which way it is? Let's see. Let's see. Do you guys see it vacuuming it up? Okay, so I blow a stream of air over the top and it vacuums it up. Wouldn't that indicate like a low pressure? Okay, so moving fluids have like a low internal pressure. I'm thinking back to this pipe system, if you're a fish swimming around, you probably feel a high pressure here and then a low pressure here, almost like you'd gone to the surface of the ocean. And now you're back in the ocean deep, even though there's no height change, right? Okay. So why is the pressure changing? Well, the best explanation, I think, is actually to start with the conservation of energy, and I'll derive Bernoulli principle for you guys. Now, you guys have seen Bernoulli principle on a PowerPoint slide, but I'm going to derive it for you guys here. Okay, and then we'll plug in stuff and apply some numbers. So I'm going to go back to a few months ago. Do you guys remember conservation of energy? Sum of energy initial equals sum of energy final. Okay. And energy can take different forms, but it has to equate because, this. You guys saw this recently too with the first law of thermodynamics. This also says that. Energy might be, for example, potential energy, mgh. It might take the form kinetic energy, 1/2 mv squared. Okay. It might take some other form. It might be in a spring. There might be some kind of work force times distance. So maybe just in general, say some kind of energy plus, right? E for some generic energy term. Okay. Okay, so different forms of energy could take. And then here's at one point in the system, here's at a different point in the system, there must be some other energy plus maybe potential energy plus kinetic energy. Let me go back and put some subscripts here. Initial, 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 final, 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 or point A to point B, initial to final, everything like that. Okay, so that's just some generic conservation of energy setup. Now, I have 6 terms here. If I divide each term by the same thing, then I do have a consistent equation. And I'm going to divide by capital V for volume. Okay, so each of those 6 terms I'm dividing by capital V volume. Okay. Now this is no longer going to be energy units. What is it going to be? All right, let's take a look. Actually, let me hone in on this one right here. This one we definitely get some insight. Who can tell me what is mass per unit volume? What is that? Density. Yeah. Like you guys remember back on Friday, I was telling you guys figure out what's the density of this. And it was some kind of like kilogram per cubic meter. That is mass per unit volume. That is density. I'll go Greek letter rho density. Right? That also shows up right here. There's Greek letter rho, that would be in the numerator, but just in general, that substitute out there. That shows up right here. Density. And that shows up here. So 4 out of those 6 terms, we're just going to pop in that density unit in place of M over V. Right? But what about the general E over V? But what is that? Well, let's see what this would be. Density times gravity times height. Oh, I remember that represented like pressure. You guys remember that? Pressure? And actually the unit for that would be Pascal if you stuck a base SI unit. Like if you go twice as deep in the pool, like if you double SH twice as deep, you would feel twice the pressure. You know, if you go deeper, you feel more pressure. Okay, so this is some kind of pressure unit. So let me rewrite this just in terms of pressure. It'd be some internal pressure. See where this is going? Plus rho GH initial plus 1/2 rho V initial squared, where this V is velocity, right, is equal to some final internal pressure plus rho GH final plus 1/2 rho V final squared. So we got 6 terms that are each pressure terms, right? These are each some number of pascals, right? Where the capital P's represent like the internal pressure. So if you're a fish swimming around in the water, you feel some kind of pressure on you. Right? Now, I know that one thing that could change the pressure is if you dive way deep down in the water. Well, that's what this term is about, this rho GH, right? Like if the H changes, that would change the internal pressure. The deeper you go, the more the pressure. Right? And also something to do with how fast that fluid is moving. Right, that V velocity, right? The faster it moves, the less the internal pressure. Right? You guys ready to apply some numbers? Right. Let's take a look at this setup. Now, this setup is a kind of a simplified example because this is a horizontal pipe. Guys, if it's a horizontal pipe, you guys say there's no height change. Okay, so there will be an internal pressure change, but not because of a height change. If there was, that would be one more complication. But what I'm trying to say here is that this H and this H are the same H. So this term and this term are just going to, we're going to take this from 6 terms down to 4. So now we're down to just 4 terms. Right? You guys that? Okay, so now we're going to say, how does the pressure change as a result of the speed change? Right? Right. I told you guys the initial pressure. Now mine says 250,000 pascals. Okay. Now, pause here, just for context. Do you guys remember in this very room right here, where we're sitting, what is the atmospheric pressure on us in pascals? 1 atmosphere is about 101,000, right, pascals? Right. Okay, so my page says 250,000 pascals. You could also call it like 2.5 atmospheres. So this is pumped up to like 2.5 atmospheres. Wonder what's gonna happen in the little skinny part of the pipe. It's gonna be less, but so start plugging in numbers. So I'm gonna do 250,000 pascals plus I'll skip past the rho GH, so 1/2 rho V squared. Rho for water, which would be 1,000 kilogram per cubic meter. Make sure you're using base SI units, so 1,000 kilogram per cubic meter density of water. The initial speed of the water, I gave you that number right here. So for me, that's 8 meters per second. And don't forget to square that, to square the speed. Okay, and that's equal to pressure final, which we're solving for. You guys remember we're trying to figure out what is the pressure in the skinny part of the pipe. And then plus 1/2 density of water, again, is 1,000 kilogram per cubic meter times V final. Now V final, V final squared, I should say, right? But V final That is your answer to the last question. That's why you need conservation of flow before you can solve Bernoulli principle. The initial speed was right here. Yeah. Okay. Who else has a question where any of those numbers come from? Any of those numbers? Yeah. Yeah, the 1,000 refers to the density of the water. It's 1,000 kilogram per cubic meter. My number 8 is my initial velocity, which is different for everybody's paper because here's your initial velocity. My final velocity is the answer to the last question. Right? How fast is it moving through the skinny pipe? Right? Which should be faster than the initial velocity. We have 2 more lines here. We'll have a bunch of Pascal numbers, and then we'll go in for the final answer. Right, so 258,000 pascals plus that is 1/2 times 1,000 times 8 squared, 32,000 pascals is equal to final internal pressure plus 512,000 pascals. Right. And then, of course, last step would just be to take this final pressure units due to motion and subtract it over. Okay, so it's 250,000 plus 32,000 minus 512,000. Looking at final internal pressure is I'm getting a negative number of pascals. Hey, can pressure go negative? How about this? We're sitting in a room right now. What if I vacuumed all the air out of this room? How many pascals of pressure would be on the walls? How about 0, right? So can pressure really go negative? Yes, for liquids. Okay. This is one of the differences between liquids and gases. Gases can go down to 0 pascals, and then you're just at a perfect vacuum. Okay. Liquids can go negative. Yeah, you can have a negative pressure. Okay. And that means that the water's actually like vacuuming on the pipe walls, like pulling on it. Something else though, you guys know something about water at low pressures. What happens when you put water in a vacuum chamber? What does it start to do? Yeah, it boils, right? It undergoes a phase change, right? From liquid to gas. Ooh, do you think it's possible you could get boiling water inside your pipe system? And would that be a bad day for this pipe system? Yeah, that's called cavitation. Yeah, that can ruin your structure down here. So if you guys are ever engineering, I should say that happens a lot in pumps. Sometimes that can like ruin the pump too, because you have like moving parts, fast moving water through narrow spaces can cause cavitation bubbles. So yeah, if you guys are ever engineering a pipe system one day, then yeah, this would be definitely something to keep your eye on. Conservation of flow and Bernoulli principle, and make sure that you aren't getting internal pressures that would boil the water in your pipe system. You guys get that? Right, so tell you what, if you feel good about all those answer choices or all your answers, all your work, then pop that in the grade tray, and I will get scores. Yeah, hang on. You're